So yes, we're going to be covering section 6.2 is our lesson today. And then tomorrow we'll do practice exercises, similar to what we did last week with section 6.1. I also do recommend that after the lesson today, you take a look at the practice problems that are in the Canvas module for 6.2, so you can get an opportunity to practice some of these things and see what you get, see what you don't get. Yeah, so I would highly recommend that. Other than that, we're gonna get this show on the road and start this presentation. I do apologize, this will be kind of dry. I'll try to get through it as entertainingly as possible, but it's just a lecture. Got to get through this stuff. Right. So here we go. Section 6.2 is on transforming and combining random variables. This is very heavily connected to stuff that we saw in, I believe it was chapter 2, with transforming and doing linear transformations on quantitative data sets. Basically follows the same rules. So some of these things we've actually seen already. We're just applying it to a new context. All right. So in this section, we're going to learn how to describe the effects of transforming random variables by adding or subtracting a constant and multiplying or dividing by a constant. We're going to find the mean and standard deviation of the sum or difference of independent random variables, and we'll find probabilities involving the sum or difference of independent normal random variables. All right, we'll see some examples of all of these things today, and then there are all of our additional resources within the Chapter 6 module, including videos, other worked examples, and notes. So don't forget about those resources. All right, so in section 6.1, we learned that the mean and standard deviation give us important information about a random variable. In this section, we'll learn how the mean and standard deviation are affected by transformations on random variables. In chapter 2, we studied the effects of linear transformations on the shape, center, and spread of a distribution of data. Recall, adding or subtracting a constant a to each observation adds a to measures of center and location. Right? Median, mean, quartiles, percentiles, those are center and location, measures of center and location. But it does not change the shape or measures of spread. Right? If it was symmetric and unimodal before it, when we add or subtract a constant, it's going to remain symmetric or unimodal. And the measures of spread, such as the IQR, standard deviation, things like that, will also remain the same. Multiplying or dividing, however, each observation by a constant b multiplies or divides the measures of center and location by b, and multiplies or divides the measures of spread by b. But still, the shape does not change. So with all of the transformations that we'll look at today, the one constant is that the shape remains the same. Whatever shape you started with your random variable, if it was skewed, if it was symmetric, it will remain that same shape throughout all the transformations. All right. Does anyone need a moment to write anything down in their notes? Right. So we'll look at an example. We have Pete's Jeep Tours. They offer a popular half-day trip in a tourist area. In order for the trip to run, they need at least 2 passengers, and the vehicle will hold up to 6 passengers. We define the variable x as the number of passengers on a randomly selected day. All right, so x can range from 2 up to 6. We can't have half of a person, so it's whole numbers here. And each of the number of passengers has the following probability of occurring on any randomly selected day. With some calculations, we'll get the mean of x is 3.75 and the standard deviation is 1.090. With that, Pete charges $150 per passenger. The random variable C describes the amount Pete collects on a randomly selected day. Right, to go from X, right, number of passengers, to C, money collected, all we do is multiply the number of passengers by the price per passenger, $150, and that converts 2 to 300, 3 to 450, 4 to 600, and so on. The probabilities of each of these amounts being collected is the same as the probability of the number of people that result in those amounts. All right, those probabilities don't need to be adjusted. We can also see that the shape remains the same, right? We can easily take this graph and overlay it on top of this one. The only thing that changes is our horizontal axis. Instead of going from 0 to 6, goes from 0 to 900. Right? It accounts for that adjustment. We also get that the mean of C is 562.50 and the standard deviation is 163.50, which we obtained simply by multiplying the mean of X by 150 and the standard deviation of X by 150. Right? And that gave us our new mean of C and standard deviation of C. So we're seeing this pattern, right? It's the same kind of ideas from our transforming of a distribution. We're multiplying by a constant, and that changes measures of center and measures of spread. So the mean and the standard deviation are both being multiplied by the 150. Right. Would anyone like a moment to write anything down from this slide? So we get the effect on a random variable of multiplying or dividing by a constant is that multiplying or dividing each value of a random variable by a number B multiplies or divides measures of center and location, mean, median, quartiles, percentiles by B, and multiplies or divides measures of spread, range, IQR, standard deviation by the absolute value of, meaning even if B is negative, right, we don't end up with a negative spread, right? Measures of spread are distances. Distances are always positive, so we multiply by the absolute value to get the spread. Right? And this does not change the shape of the distribution. Again, it will shift the distribution a little bit. The range will get bigger, right? But the actual shape itself remains the same. As with data, if we multiply random by a negative constant B, our common measures of spread are multiplied by the absolute value of B. Again, what I did. Right. So any questions so far? We need a moment to write any of this down for their notes. Please raise your hand. All right, we just won't keep on swimming then. Adding a constant to a random variable. All right, now we'll consider the same context. We have Pete's Jeep Tours again. We defined C as the amount of money Pete collects on a randomly selected day. Here's that same probability distribution. And the mean and standard deviation. It costs Pete $100 per trip to buy permits, gas, and a ferry pass. The random variable V describes the profit Pete makes on a randomly selected day. So now we have another probability distribution reflecting the profit on a randomly selected day, and that can range from 200 to 800. And again, that's simply found by subtracting 100 from the amount of money collected. And once again, we see that the probabilities just essentially transfer over, right, and remain the same essentially. And once again, we witness that the shape did not change. This graph looks the same as this graph, right? The only difference is, again, the horizontal axis changes to represent the new range of values based on the transformation. The mean of our new random variable v is 462.50, 562.50 minus 100. The standard deviation is the same. All right. Why do you think that our spread didn't change? Does anyone have an idea why the spread remained the same? Our standard deviation remained the same, even though we did a transformation. Consider the fact we subtracted the same number from every possible outcome. So the difference from 300 to 900 is the same as the difference between 200 to 800. The spread of my data hasn't changed at all, so the standard deviation is not going to change. We've simply shifted the histogram down a little bit because we subtracted money. Would anyone like a moment to write anything down? So then we come to this conclusion: the effect on a random variable of adding or subtracting a constant, adding the same number, a, which could be negative, to each value of a random variable, adds a to measures of center and location, mean, median, quartiles, and percentiles, but does not change measures of spread, range, IQR, standard deviation. It does not change the shape of the distribution. So again, adding or subtracting changes measures of center and location, has no change on measures of spread, and does not change the shape. Would anyone like a moment to write any of this down? So then we've multiplied, we've added, we're up to a linear transformation. The effect of a linear transformation on the mean and standard deviation. If y equals a plus b times x is a linear transformation of the random variable x, then the probability distribution of y has the same shape as the probability distribution of x. That's why those probabilities don't change on the table. The mean of y is equal to a plus b times the mean of x, and the standard deviation of y is equal to the absolute value of b times the standard deviation of x. And again, we use the standard or the absolute value of b because b could be a negative number. Right? We can't end up with a negative standard deviation. Linear transformations have similar effects on other measures of center or location, median, quartiles, percentiles, and spread, range, and IQR. Whether we're dealing with data or random variables, the effects of a linear transformation are the same. Please note, these results apply to both discrete and continuous random variables. It doesn't matter if it's discrete or continuous. The rules of linear transformation still apply the same to both. Are there any questions so far? So now we can combine random variables. Many interesting statistical problems require us to examine two or more random variables. Okay, let's investigate the result of adding and subtracting random variables. Let X equal the number of passengers on a randomly selected trip with Pete's Jeep Tours, and Y equal the number of passengers on a randomly selected trip with Aaron's Adventures, another tour company. Define T to equal X plus Y, right? So number of passengers on a randomly selected day between both tour companies. What are the mean and variance of T? Here's the probability distribution for X, and we have the probability distribution for Y, all right, with the mean and standard deviation for both as provided, and we have our histograms. Since Pete expects 3.75 and Aaron expects 3.1 passengers on any randomly selected day, they will average a total of 3.75 plus 3.1 equaling 6.85 passengers per trip. We can generalize this result as follows. For any two random variables, x and y, if t equals x plus y, the expected value of t is equals the mean of t equals the mean of x plus the mean of y. In general, the mean of the sum of several random variables is the sum of their means. Right, so if I want to know the expected value when adding two random variables, I just take the mean of each and add them together. Right, there's no fancy calculation, it is just add them up. How much variability is there in the total number of passengers who go on Pete's and Aaron's tours on a randomly selected day? Well, to determine that, we need to find the probability distribution of T. All right. Would anyone like a moment to write anything down from this particular slide? Please raise your hand. All right. Well, when combining random variables, the only way to determine the probability for any value of t is if x and y are independent random variables. Right? If knowing whether any event involving x alone has occurred tells us nothing about the occurrence of any event involving y alone, and vice versa, then x and y are independent random variables. Right. Probability models often assume independence when the random variables describe outcomes that appear unrelated to each other. You should always ask whether the assumption of independence seems reasonable. Right. In this case, it's reasonable to assume x and y are independent since these tour companies operate in different parts of the country, right? Because someone signed up for one of Pete's tours has no effect on whether or not someone's signing up for one of Aaron's tours. Right? They're in different areas, they're not taking business from each other. So it's reasonable. Right? So then we can determine the probability distribution. This table shows all the possible combinations of passengers between the two companies. Right? We can have 2 and 2, 2 and 3, 2 and 4, 2 and 5, so on and so forth, and we can have all the different combinations. When adding the passengers, right? So 2 from Pete's, 2 from Aaron's, we get 4 passengers total. The probability of hitting 4 passengers total, right, is the probability of 2 from Pete times probability of 2 from Aaron. We get 0.045. Okay, these are this is based on what we learned in probability from chapter 5. Right. It's the probability of both things happening. It's an AND calculation. All right. So we get all this. We also already determined that the expected value of t, or the mean of t, is 6.85 based on the addition of the two means from x and y. We can then calculate the variance based on our probability distribution, right, which is adding up the difference between each outcome of t minus the mean of t squared times the probability of each of those outcomes, which we have up here. We get all this kind of crazy calculation, and we end up with a variance of 2.0775. However, something interesting has occurred. Right? The variance for x was 1.1875, and the variance for y was 0.89. Right? While we didn't get these directly, if we square the standard deviations of both distributions, we end up with these two numbers. All right. The interesting thing is 1.1875 plus 0.89 gives us this result. Gives us the variance of t, right, 2.0775. This is a consistent result when adding random variables. The variance, right, ends up being the sum of the variances of the random variables you're adding. Right. When we add two independent random variables, the variances add. Standard deviations do not add. That's why we didn't show standard deviations being added. It is not a thing. For any two independent random variables, x and y, if t equals x plus y, then the variance of t is variance of t equals variance of x plus the variance of y. In general, the variance of the sum of several independent random variables is the sum of their variances. So even if I had 3 random variables or 4 random variables that I was adding all of those up, I can find the variance of the total of all of those by adding the 3 or 4 different variances. So I don't have to do all of that calculation of actually calculating each variance with probability distribution and all that stuff. If I know they're independent, I can just add them up, save some time. Remember that you can add variances only if the two random variables are independent, and that you can never add standard deviations. That's not a thing. They do not add up that way. You got to add the variances, then you can take the square root of those added variances to get the new standard deviation. So we need a moment to write anything down from this slide. Okay. We can also perform a similar investigation to determine what happens when we define a random variable as the difference of two random variables. In summary, we find the following. So we could go through an entirely new example and show subtracting, but we'll just go over the results. The mean of the difference of random variables for any two random variables, x and y, if d equals x minus y, then the expected value of d is the expected value of x minus expected value of y. Just subtract the means. Again, there's nothing fancy. If I want the mean of the difference between these two, I just subtract the two means. In general, the mean of the difference of several random variables is the difference of their means. The order of subtraction is important, as in with all math, right? 5 minus 2 is not the same as 2 minus 5. Right? If it's saying that d is defined as x minus y, you need to subtract things in that order. The mean of x minus the mean of y. You cannot do the mean of y minus the mean of x. That's not how it was defined. You'll get the wrong answer. Now the variance is a little different here. It's a little unique. For any two random variables x and y, if d is defined as x minus y, then the variance of d is still the sum of the variances. Right? When I subtract two random variables, I still add their variances. Okay. In general, the variance of the difference of two independent random variables is the sum of their variances. Right. So again, even if I'm subtracting random variables, I will still add the variances. Right. Is there any questions about this? Would anyone like a moment to write anything down? Please raise your hand. All right. So now combining normal random variables. So again, now we're switching to normal because those have special properties. If a random variable is normally distributed, we can use its mean and standard deviation to compute probabilities. Any sum or difference of independent normal random variables is also normally distributed. So if I have two normal random variables and I want to add them or subtract them, the result will still be normal. So I can use all the things I know about normal distributions, right? Table A, probabilities, all that stuff with the results. So here's our example. Mr. Starnes likes between 8.5 and 9 grams of sugar in his hot tea. Suppose the amount of sugar is in a randomly selected packet follows a normal distribution with mean 2.17 grams and standard deviation 0.08 grams. If Mr. Starnes selects 4 packets at random, what is the probability his tea will taste right? So we'll let X equal the amount of sugar in a randomly selected packet. Since we're selecting 4 packets, we're adding 4 of those same random variables. Right, so we get then T is defined as X1 plus X2 plus X3 plus X4. Right? The first randomly selected packet, second randomly selected packet, third and fourth. We want to find the probability that T is greater than or equal to 8.5 and less than or equal to 9, right, within the acceptable range. So we find the mean of our random variable T by adding the means of each random variable X. It's all the same random variable, so we're just doing 2.17 added to itself 4 times. We get 8.68 as the mean for T, or the expected value for T. We then use the fact that we can add variances. Again, we're not adding the standard deviations. We're given the standard deviation. And remember, the standard deviation is the square root of the variance. So if I want the variance from a standard deviation, I square the standard deviation. So to get our variance, we add 0.08 squared 4 times, and we get 0.0256. And then we convert that back to the standard deviation, and we get the square root of 0.0256 equals 0.16. Okay, so now we have our mean and standard deviation. Once we have those, we have all we need for a normal distribution, right? We could sketch the graph. We can now use table A. We can standardize our numbers and get our results, right? Which is here. We have our sketched distribution here. We want between 8.5 and 9 grams. So it's the shaded area. We first need to standardize our lower and upper bounds, right? And we end up with negative 1.13 for the lower bound and 2 for the upper bound. The probability of Z being greater than or equal to negative 1.13 and less than or equal to 2.0 is 0.9772, which would be the probability of having a Z less than or equal to 2, minus 0.1292, which is the probability of Z being less than or equal to negative 1.13. So we subtract this one from that one, we get 0.8480 from table A. This is all getting from table A. There's about an 85% chance Mr. Starnes' tea will taste right. So again, we're using table A again, Again, there's going to be lots of practice using these things, so you need to make sure to take advantage of them. And if you don't understand, you need to ask and let me know so I can do better. All right. Is there any questions about this example? And does anyone need a moment to write anything down? Right. In summary, in this section, we looked at examples on how to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant, finding the mean and standard deviation of the sum or difference of independent random variables, and finding probabilities involving the sum or difference of independent normal random variables. All right. And that is, in sum, section 6.2. All right. That's the whole thing. So I do recommend going to Canvas, look at the notes, look at the other resources if you'd like to see other examples for transforming and combining random variables. And I highly recommend looking at the practice problems and seeing if you can solve some of them. You know, try a couple. You don't have to do them all. You don't have to turn them in, but I do recommend trying a few. Right, get some practice in. Other than that, tomorrow in class, we will be doing some examples as a class, doing some work so we can get a little bit out of this lesson. And yeah, that sums it up for today. If you have any questions, please let me know. Otherwise, you guys are free to go, and I'll see you tomorrow morning. Same bat time, same bat channel. Have a lovely day. That's it. That's all I got.